super easy trick to learn crystal field theory. Firstly, let me teach you that what is a crystal field theory. Well, consider a d block element like cobalt. We know that cobalt has 5 degenerate orbitals. On the other hand, consider that a strong ligand like NH3 approaches near the cobalt in order to form coordination compound. Now listen carefully. As a result of this approaching ligands, the 5d orbitals of cobalt will split into 2 sets. Let me repeat it. As a result of this approaching ligand, the 5d orbitals of cobalt will split into 2 sets. Now here is one important question which you must learn. Why the 5d orbitals of cobalt split into 2 sets in the presence of a ligand? Well, it is crystal field theory which explains this phenomena. It is because of electrostatic interaction between a metal cation and a ligand that these 5d orbitals split up. For example, it is crystal field theory that teaches us every metal cation like cobalt is acting as a positive charge and every ligand like NH3 is acting as a negative charge. Due to electrostatic force between these two species, the 5d orbitals of cobalt split up or back down. So remember that it is crystal field theory which explains that how these 5d orbitals split when a ligand approaches near a metal cation. Now to learn crystal field theory completely, firstly we have to learn the shapes of d orbitals. We know that d orbitals have 5 degenerate orbitals like dxy, dyz, dxz, dx squared minus y squared and dz squared. Here, I will teach you my personal and easy way of drawing the structures of these 5 orbitals. In case of dxy, firstly, I draw x-axis and then y-axis. Remember that it is up to you whatever axis you select. We know that the shape of d orbital is like double dumbbell. I draw the lobes of double dumbbell between the axes. In case of dyz, I draw y-axis and then z-axis. I draw the lobes of double dumbbell between the axes. In case of dzx, I draw x-axis and then z-axis. I draw the lobes of double dumbbell between the axes. In case of dx squared minus y squared, I draw x-axis and then y-axis. Here, this squared on x and y reminds me to draw the lobes directly on both the axes. So I draw lobes of double dumbbell on the axis. In case of dz squared, I only draw z-axis. This square on z-axis reminds me to draw one lobe on axis and put a ring at the center. So these are the structures of 5d orbitals. Now here are some key concepts which you must understand, otherwise you will not understand crystal field theory. Firstly, in case of these 3 orbitals, the lobes of orbitals are between axes. For example, like this lobe, and like this lobe. Secondly, in case of these 2 orbitals, the lobes of orbitals are along or on the axis, like this lobe or this lobe. Now if I ask you about tetrahedral complex and octahedral complex, can you answer it? Well, the easy trick is, I select this T in tetrahedral and I write it as a 4, while I select O in this octahedral and I write it like 6. So in tetrahedral complex, central metal atom is surrounded by 4 ligands, like COCl4 -2, while in octahedral complex, central metal atom is surrounded by 6 ligands, like CONH36 Cl3. Now listen carefully. In case of tetrahedral complex, ligand approaches between axes. Let me repeat it. In case of tetrahedral complex, ligand approaches between axes. I mean, in tetrahedral complex, ligand will attack on this lobe or on this lobe or on this lobe of orbitals. After attack, there will be interaction between electrons of ligand and electrons of orbitals. Remember that when there is interaction between electrons, energy of orbital increases. Let me repeat this important point. When there is interaction between electrons, energy of orbital increases. Thus we learn that energy of these three orbitals increases and energy of these two orbitals decreases in case of tetrahedral complex. On the other hand, in case of octahedral complex, ligand approaches along axis. I mean, ligand will attack on this lobe or on this lobe of metal orbital. After attack, electrons of ligand and metal orbitals will interact, hence energy of these two orbital increases. Thus we learn that energy of these two orbital increases and energy of these three orbital decreases. Thus note down all these important points. Now let me teach you crystal field theory for octahedral complex. We already learned that in case of octahedral complex, energy of dx squared minus x squared and dz squared increases. Consider 5 degenerate orbitals of a metal atom. Let a strong ligand like NH3 approach near this metal atom. The average energy of these 5d orbital increases. Here, a lot of students do not understand that why energy of these 5d orbital increases. Well, I teach them a simple example. I say, when you are in danger, your adrenaline level pumps up and you get ready. Similarly, when ligand comes near to a metal atom, the 5d orbitals get excited and their average energy increases. Remember that I use the word average energy. Now when ligand interacts with 5d orbitals, they split into two sets. We already learned that in case of octahedral complex, energy of dx squared minus y squared and dz squared increases from average energy level because ligand like NH3 will attack along axis, while the energy of dxy, dyz and dxz decreases from average energy level. We call this set of energy as Eg and we call this set of energy as T2g. Remember that the energy of Eg increases from average energy level, so its value is positive 0.6 delta. Secondly, the energy of these three orbital decreases from average energy level, so its value is negative 0.4 delta. We can see that this is the energy gap between these two sets of orbitals. We call this energy gap as crystal field splitting energy or CFS energy. Here is one important point which you must remember at any cost. Consider a strong ligand like NH3 and a weak ligand like H2O. When a strong ligand like NH3 approaches near 5d orbitals, the energy gap between these two sets of orbitals will be large. We call it as a strong field complex. On the other hand, when a weak ligand like H2O approaches 5d orbitals, the energy gap between the two sets of orbitals will be smaller and we call it a weak field complex. Now let me teach you the electronic configuration. For example, consider that iron atom react with a strong ligand like NH3. We know that iron has 6 electrons. Firstly, I fill the orbital by 1 electron. 1, 2, 3. Now the energy gap is very high between these two sets. So the 4th electron will stay in this orbit, the 5th electron will stay in this orbit, and the 6th electron will stay in this orbit. Now to write the electronic configuration, we know that in T2g there are 6 electrons. So this is the electronic configuration for this system. Secondly, we can see that in this system, the electrons are paired, so it is dimagnetic in nature. Remember that in octahedral complex, a fourth electron enters to Eg, it is a high spin complex. A fourth electron enters to 2G, it is a low spin complex. Here, fourth electrons enter to 2G, so it is a low spin complex. On the other hand, consider that iron reacts with a weak ligand like H2O. We know that there are 6 electrons in its d orbital. Firstly, I fill the orbitals by 1 electron. 1, 2, 3. Now the energy gap between these two sets is very small. So the fourth electron will stay in this orbital. The fifth electron will stay in this orbital. Now all the orbitals are filled. I will start refilling the orbitals. I place the sixth electron in this orbital. Lastly, I write the electronic configuration for this system. We can see that there are 4 electrons in T2G and 2 electrons in Eg. I write T2G4 and Eg2. So this is the electronic configuration of this system. Secondly, we can see that there are unpaired electrons present in this system. So it is paramagnetic in nature. Here, the fourth electron enters to Eg, so it is a high spin complex. Therefore, using this trick, we can easily draw CFT for octahedral complex. Finally, let me teach you CFT for tetrahedral complex. We already know that the energy of dxy, dyz and dxz increases in case of octahedral complex. Now consider 5 degenerate orbitals. Let a strong ligand like NH3 approach near these orbitals. Their average energy increases. After interaction, these orbitals split into 2 sets. The energy of dxy, dyz and dxz increases, while that of dx squared minus y squared and dz squared decreases. This set is T2G and this set is Eg. The energy of T2G increased, so its value is positive 0.4 delta. And the energy of Eg decreases, so its value is negative 0.6 delta. We can see that this is the energy gap between these two sets. We call it as crystal field splitting energy. Also, it is a strong field ligand. Now consider a weak ligand like H2O. We know that in case of a weak ligand, the energy gap between the two sets of orbitals will be smaller. We call it weak field ligand. Now let me teach you the electronic configuration. Consider cobalt react with NH3. We know that it has 7 electrons in its orbital. Firstly, I fill the orbitals by 1 electron, 1 and 2. Now the energy gap is very high between these two sets, so the third electron will stay in this orbital. The fourth electrons will stay in this orbital. Now these orbitals are filled. The fifth electron will jump to this set. The sixth electron will stay in this orbital and the seventh electron will stay in this orbital. I write the electronic configuration which is equal to Eg 4 electrons, T2G 3 electrons. Secondly, the electrons are unpaired, so it is paramagnetic in nature. Remember that in case of tetrahedral complex, if third electron enters to T2G, it is a high spin. If third electrons enter to Eg, it is a low spin. Here, third electrons enters to Eg, so it is a low spin complex. On the other hand, consider that cobalt reacts with weak ligand like H2O. We know that there are 7 electrons in its orbital. The first electron will stay here and the second electron will stay here. Now the energy gap between these two sets is very small. So the third electron will stay here, the fourth electron will stay here, the fifth electron will stay here. Now I double fill the orbital. the sixth electron will stay here and the second electron will stay here. Now I write the electronic configuration. Eg 4 electrons, T2G 3 electrons. Secondly, the electrons are unpaired, so it is paramagnetic in nature. Here, the third electrons enter to T2G, so it is a high spin complex. Therefore, using this super easy trick, we can easily understand and learn crystal field theory.